So what does forming polymers from each of these monomers actually look like? Well, let's start with carbohydrates, which for our monosaccharides, that would be the monomer of carbohydrates. Here we have a carbohydrate monomer, again, also called a monosaccharide, and let me just copy and paste that here. There we go. So now we have two monomers, two monosaccharides. Now, to make a polymer or a carbohydrate, we would need to bond many of these together. But for the sake of simplicity, here's how it's going to look if we are just looking at how to bond together. Sound good? So imagine what I'm showing you, but on repeat, over and over and over. Basically, what would happen is we have this hydrogen atom here from one monosaccharide. It would be removed along with the hydroxyl group here of the other monosaccharide, and then these would form water. And this would allow the two monosaccharides to then form a covalent bond with one another like so. And so keep in mind, this oxygen that I'm pointing to is the same as the oxygen up here. The covalent bond that we made is actually the bond that's just to the right of this oxygen. It's linking the two monosaccharides together. Moving on to proteins, where amino acids are monomers, this right here is the general configuration of an amino acid. And again, I'm just going to copy and paste a second one here. Here is what the dehydration reaction would look like. There goes water, and then here we have our covalent bond right there forming between the two monomers of the two amino acids. All right, so moving on to nucleic acids, again, our nucleotides are monomers for nucleic acids. This is the general configuration of a nucleotide with our sugar, a nitrogenous base, and a phosphate group. Now, the phosphate group I represented by the letter P, and most people do that where they have the letter P and then a circle around that letter. However, I gave it some space here because something that's important to remember is that phosphate groups are not just phosphorus. They have phosphorus and oxygen molecules. The important bit is this hydroxide here. And so here, let me go ahead and copy and paste a nucleotide again. And now let's go ahead and follow the dehydration reaction and how it would look like here. There goes water, and here we have our covalent bond forming between our two nucleotides. And again, remember that a chain or a polymer of anything is usually more than just two. I just only have space right here to draw out two for you. Sound good? But this would repeat down the line to make nice long chains of nucleotides all bound together to make a nucleic acid. Okay, but wait, don't you tune out yet. There is more. What about lipids? Well, let me erase all this right quick. Now, lipids are a bit odd, a bit different. Lipids are made up of glycerol, which looks something like this. You've got carbons and hydroxyl groups all bound together. And then lipids are also made up of fatty acids, which look something like this. And then you'll notice I am drawing in some dotted lines right here. These dots just represent more carbon bound to two hydrogen atoms going along that chain. Fatty acids can be varying lengths and sizes, and so this is just showing X number of carbon and hydrogens going down this chain. Now you'll notice here that glycerol seems to have 3 available spaces, and you'd be correct. To actually make a triglyceride, or an actual functional lipid, there needs to be at least 3 fatty acids per 1 glycerol. So let me go ahead and copy and paste those. Okay, now, how do we combine the glycerol with the fatty acids to make a lipid? Notice anything interesting on the screen? Right, these molecules combine through dehydration reactions too. So it's going to look something like this, where there goes water, but this times 3. And here we have now 3 covalent bonds. Now remember, even though lipids use dehydration reactions to form covalent bonds, and they also use hydrolysis reactions to break those bonds, lipids do not actually fit the monomer to polymer model that we've been using because it's not the same subunit repeated over and over to make a lipid like it is for carbohydrates, nucleic acids, and proteins. Make sense?